Hey, Dr. B here, and let's take a look at some organic physical properties. We're going to show you a lot of different data, and what I want you to focus on is the idea that physical properties are always due to breaking or forming the intermolecular forces between molecules. It's a physical property. That means we'll never be breaking the bonds within the molecule. That would be a chemical reaction. But if something is to melt or to boil, we need to either partially or fully overcome the intermolecular forces that exist between molecules. Watch the screencast on that topic if you need to, because we're going to be really just applying that knowledge. Here's a homologous series of alkanes going from methane to decane, and the boiling points as well as the melting points increase as you go up the ladder. So boiling and melting point are observed to increase with a chain length, and that's not so surprising since for each molecule the number of intermolecular forces is increasing, and perhaps there's some tangling going on as well once you get to these large flexible hydrocarbon units. So the total energy would be higher to break them per molecule, therefore the boiling point and the melting point will increase. No surprise, really. Here's some isomers of C5h12, right? We can either make it a straight chain or we can branch it, and the boiling point is going down. So the boiling point observed to decrease with the branching. The explanation is that some of these intermolecular forces are either fewer or less accessible. And so you can have less accessible intermolecular forces, hard to get at that hydrogen, for example, if you take a look at that molecule and you actually draw it out. Also, these can't tangle as much once they get ball-shaped. So either can lead to lower boiling points as you get more branching. Here's some more data. Now we do have the homologous series for each type of functional group. I don't want you to focus on that as much, but just work your way down here. And it's not a pattern that's constantly going up or down, but it's due to a clear thing. Look at that one, much higher, and much higher here, and here it's pretty low. What's going on is the intermolecular forces for some of these are very strong. Without going into hydrogen bonding in complete detail, if you have an OH or an NH, well then hydrogen bonding with itself or with water is possible. And in this case, we're talking about it with itself. So it's hard to break these bonds because they can hydrogen bond with each other. Therefore, boiling point does increase with the functional group polarity, especially if it can hydrogen bond. You have stronger intermolecular forces. This also plays a direct role when we look at solubility. Now here's some substances here: ethanol, 2-carbon alcohol, 3-carbon alcohol, 4-carbon alcohol, 6-carbon alcohol, and I suppose that's a no-carbon alcohol, isn't it? It's just water. And what you observe is that up to here it's water soluble, but once you go to butanol or higher, it's water insoluble. A quick explanation would be that to say, hey, it's getting greasier. These hydrocarbon chains are essentially grease, and once it gets greasy enough, it pops out of water. Another way of explaining it is that alcohols can hydrogen bond with water, and so you can get favorable hydrogen bond interactions. That's why these are soluble with water. But as the hydrocarbon chain gets longer, there's not favorable intermolecular forces with water on the greasy side, and therefore at some point it gets water insoluble and forms 2 layers. So solubility would be greatly aided by when you have hydrogen bond forces, but it's reduced when you have greasy hydrocarbon regions. And the magic number typically for an alcohol is once you get 4 carbons per OH or more, well, that thing's going to pop out of water. This is an introduction to organic physical properties.